Okay, the second lab is for the Centroid and then moment of inertia. I believe that you guys already learned about this in the strength material. So I'm not probably go too much of detail, but I'm going to try to refresh your memory about it. And then during the lab, you will probably create something with a CAD, AutoCAD maybe. I think most of you guys took AutoCAD, right? AutoCAD, and then you create it, and then let the AutoCAD calculate the Centroid, and you compare your own with your own calculation to see if it is all matching together, right? So that's the lab. But before we do this, before we actually do the lab, I'm gonna give you some to refresh your memory, give you some theory behind it. So the Centroid. And the moment of inertia. And this guy right here, especially the moment of inertia, is very important when we measure the strength of the material. So if you remember the first lab that we did, I was trying to explain a little bit about the sigma design and the sigma actual, right? So sigma design is usually coming from the material of your choice, SY. What was SY? SY was what? Yield stress divided by what? N, right? Safe factor. That gives you the design sigma, design stress. And then the actual stress is coming from the design that you actually created. For example, if you have some force applied on an area, it gives you the sigma actual developed inside of internally, right? And then when it comes to design, our goal is to make sure that sigma actual is always lower or higher than sigma d. Which one? Lower or higher? Sigma actual has to be lower than sigma d to be on the safe side, right? That's basically the whole purpose of design. And then in order to make the whole thing most economical, we try to equalize. That's optimal design, okay? So to actually make the most profit out of your design, we try to use your reference, sigma d, to create your own product, right? That's what we do. But in this case, if you remember, for a beam design, this is F over A, just simple stress for a case like the square receiving a force on it, F with the area A. Then it's going to create sigma actual. But if you are talking about beam like this with F, it's simply supported beam, if you remember, this will create stress like this, right? Stress, if you remember. If you draw a bending moment diagram, we will do it later, but bending moment diagram will give us the sigma actual, the maximum sigma, as a form of what? If you remember the equation for sigma actual, what was it? Moment n, and then C over. Anyone remember? Nobody remember? MC over I. Okay. So this actually is the equation that allows us to estimate the sigma actual for a beam structure like this. And this is very important because when you're designing, for example, a vehicle, the most important component that goes into the vehicle is what? The frame. Frame has to be sturdy to build things up on it, on top of it. So beam design is so important. And if you see this equation, what is I right here? What was I? Moment of inertia. So if I goes up, sigma goes down or up. If I goes up, sigma goes down, right? If the denominator goes up, this guy goes down. Meaning that we should be able to somehow design this I or determine this I to be largest to make sigma actual lowest. Which one is better? Lower sigma actual or larger sigma actual? Lower, because if it is lower, you may end up having what? Cheaper material. Cheaper means you can save money, meaning you can feed your family more, right? You can make actually more profit. So we always try to make the sigma actual lowest but that means that we need to try to make I the highest. How do I make it highest? That's what we will study today, but I guess you already have done this before. So I'm trying to refresh your memory quick, all right? So, but the thing is, in order to calculate moment of inertia, you should be able to calculate what? Centroid first. Because this guy will be defined by the centroid. If you don't know the centroid, there's no way for us to calculate moment of inertia. But that's basically the whole story behind. Okay? So we should know where we are going. This is where we are going. The design procedures that you have to know. In order to do so, you need to know what is important, right? What is important to be able to optimally design your parts. And in that process, there are some factors like I right there. You should be able to calculate. So if you don't know how to calculate, there's no way you can do all this design process, right? So design process only depends upon all these important factors that you need to know. Just let's refresh your memory. N, what was N? Moment. C. The distance from the centroid to the outermost surface is C. Okay, so that means that the highest level of stress is going to occur on the surface on this top surface or bottom surface. So if you happen to have a crack on the surface, that crack could be increasing. If you are receiving the repeated load, that micro crash on the surface, because as I said, the stress is going to highest on the surface. For example, if you draw the stress distribution, it's going to be something like this. Highest. If you push it down, what is the stress level on the surface? Is it contraction or extension? Contraction, because if you push it, right? At the bottom, what is it? If you push it down, it's going to be expanded. So it's an extension, right? Extension. But this is basically the stress magnitude if you happen to measure the stress along this across this area. Okay. So we will probably discuss about the fatigue later, but this is an important aspect of what's really happening when you are loading something like beam with a load of F force. Okay. But again, in order to estimate all this, you need to know this first. So let's study a little bit about the centroid and then the moment of inertia. So centroid is nothing more than just what is it? Point. So that is just defined as the point where about the area could be, about which the area could be balanced. How many of you play basketball? And then you know how to do the balancing with the point? So that's the point where once it is rotating in balance, that point that your fingers are pointing or holding, that's the centroid right there. Centroid. So we need to know how to calculate centroid first. So centroid is defined by the equation of A T y bar is equal to sigma A I y I. We use the concept of the area moment. Area moment is nothing more than just area times the distance. If you remember the moment, what is the moment? The definition is force times distance, right? That's the moment. We use the same concept to find out the centroid by using this equation, which is a moment equation. Area moment. Okay, this is area moment. Area moment. And what it says is that if you collect the area moment for very small pieces on the entire shape, it's going to be the same, equal to the entire area times centroid. So y bar right here is centroid. This is centroid right here. So the moment has to be, area moment has to be equal. Meaning if I have a shape like this, and if you divide the whole thing into small pieces, and with a reference point, that this is a reference line, if you calculate AI, YI, for example, this is A1, A2, all the way to A12. This means that you multiply the area with the YI, which is the centroid. This is a centroid for each individual. This is a centroid to each area. So we know the centroid of this guy at the center right here. And YI is defined by this. Y is Y1. And Y2 is the same, Y3, Y4, Y5 is right here. It goes like this. So if you multiply the area of each piece times the centroid distance from centroid to the reference line, YR, it has to be equal to total area. Total area A is nothing more than the sum of AI. Y bar is the centroid of the entire area. So entire area should be somewhere around here. So in order to find Y bar, you just have to simply take AT to the right hand side. So that means you have AI, YI over AT. That's your centroid equation, right? If you remember? I think you have seen this before, but just as a quick refresh of your memory, that's basically the definition. So by using this definition, we can actually find the centroid for any complex shape. So I'm going to do some exercise, and then I'll probably assign some homework, okay, next time. So for example, if I have a shape like this, this is your new house, and then it has a dimension 60 millimeter, 10 millimeter. Okay, so, and then the length will give there. So we have all the dimensions right here. And then the one in the middle is a window. This is empty right here. So everything is solid except this small one in the middle. So how do I calculate this centroid? How do I calculate? Well, it looks like it's a little bit complicated. Simple house, but still complicated. So whenever you're facing a complex shape like this, what is the best strategy?
Breaking up pieces.
Yeah, the divide and conquer, Roman strategy, right? Divide and conquer. So basically, what we can do is make the whole thing into pieces, 3 pieces. One is this one right here, the body. Number 2 is window. Number 3 is roof. So I can divide the whole thing into a rectangle, smaller rectangles around, which I know about its centroid already. I don't know the centroid of the whole thing, but I know the centroid of the small pieces, right? The rectangle is just easy. It's just half of the height is a centroid. That's already known. So by using this equation right there, I can actually try to find out the Y bar. So the first thing is that you can actually make a small table, 1, 2, 3, and then you calculate AI, the YI, and then area moment, AIYI. Okay, so you basically just to fill this out so that you can actually use this equation right here to find out your centroid. That's kind of the easiest way to minimize your error. All right? If I do so, just list up number 1. Area number 1 should be, what is it? 50 times 40. So 2,000. And then number 2, that's 50 times 20, right? So 600. However, because there's a window or empty space, I'm going to put negative right there. Okay? And then number 3 is the roof, 60 times 10, 600. And then I just need to find out the yi, the distance between the centroid of each area to the bottom line, the reference. This is the reference right here that I'm going to use to apply the area moment. Whenever you see the term moment, you need to have a reference. Okay? Because in order to apply in order to calculate a moment of a force, you basically calculate a moment for a certain reference point. If you don't have a reference point, there's no way for us to calculate the moment. So here, I'm going to actually find out yi for the number 1, which is this guy. It should be what? Half of this 50, right? The centroid, the distance from centroid to the reference, so 25. How about number 2? Number 2 is right here. And then the centroid of this guy is half of it, which is 10. But from the reference point, you have to add this up right here. So it has to be 15. How about number 3? Half of the height should be 5 plus 50. So 55. That's easy enough. So it looks like it's a little complicated, but I mean, if you do this math and then fill this out, it's very easy. Fill it up, and then use that equation. So now I just have to multiply this together. If you multiply area and y, that's 50,000, negative 9,000, 33,000. One thing you have to make sure is that the roof is very small area, but because it is far away from the reference point, the area moment is pretty high, right? So moment is basically proportional to distance, okay? So even if you have a very small force, if you are referring to a reference point far away, then your moment will go up. Now I just have to add this up to find out the numerator right here for this equation. So if I add this up, how much is it? 74,000. So that goes right here. And then the AT is nothing more than what? Just summation of all this area, right? And then because these are canceled, you have 2,000. Right? That's your y bar. So y bar is nothing more than 37 millimeter. 37 is somewhere around here. That's how you calculate your centroid, right? Everything clear?
Yes.
Any question so far? Any question? No? So why do I do this? Why do I need this? Well, in order to calculate what? Why do I calculate this? To calculate moment of inertia, right? Moment of inertia. So let's just now take a look. How do we calculate moment of inertia? Okay. Any question? Can I erase? Okay, the moment of inertia this is Okay, so the definition is just, it is the sum of the products. You actually collect all the product by the multiplying each infinitesimally small element of the area with the square of its distance from the centroid. So basically, if you see the definition of the MOI, it has the centroid in there, embedded. So that means that if you don't know how to get the centroid, there's no way for us to calculate MOI, moment inertia. Okay, that's why. So depending on you change the reference, depending on the centroid, the moment inertia will change. So by definition, I is going to be defined by summation sigma of y squared dA. So dA right here is a small area, infinitesimally small element. That's dA right here. And then y right here is the y squared is square of the distance from the central. That's y. Okay. And then we define I as just like this. This is a definition. There's nothing more than just definition. Somebody actually calculated sigma actual. They found that it is mc over sigma y squared dA. And instead of using this equation, they just defined this as I. Okay? So the calculation first, definition second. So basically that's where it came from. Okay? Make sense? So with this now, I think you guys know that the, I don't know if you remember this, square centroid is in the middle. Height with the base, B. If you remember the I, what was I here? Remember the I for the square? BH cubed over 12, yes, 12. Okay. If this is a strength material, I'm going to show you where this equation came from, but I'll just skip it. But again, this equation is from the definition. This side right here. If I give you a quick review, I is nothing more than, so you're basically coming from, this is negative h over 2, this is positive h over 2 from the centroid. So from h over to negative, h over to positive, y squared. Y squared is any distance from the centroid to a small area here. Say this is your small area. And then y is distance from the centroid to the small area. But y squared times dA. Okay? That's that. By definition, this is the equation. And if you expand this a little bit, it's going to be just nothing more than y squared. dA is not dA is what? dA is simply just b times height, which is dh along h, there's small d. So b times small d, dh, okay? Or dh, I'm sorry, not dh, dy, has to be dy, because we use y right there for the distance along y direction. So by solving this, d is going out, and then the y, what is the integration of y squared? What is the integration of y squared? 1 over 3 y cubed, right? Coming from negative h2 to positive h2. So if you plug this into right there, you're gonna have this. That's where it came from. Okay, so just a quick review on it. And let me see. And then also the popular equation for circle. Remember circle? With the what is it? diameter D, if this is known, I for the, if you remember I for the circle, what is it? Remember? Pi D. I d to the fourth over 64, I guess. 64. This is the equation for the circle, right? Moment of inertia for the circle. And then the way they calculate this again is that they use the same equation. Okay? But instead of using that one directly, by using y directions, it's much easier for us to